Hi everyone, this is Coco and I'm Larry. So our project is about Dota 2, which is a 5 versus 5 computer games. So there will be 2 teams and each team has 5 different heroes. One of the team will finally win. So our goal is to predict the winning team with the given features. Part 1 is we only depends on the 10 picked heroes. On part 2, we add 2 more mid-game features, that is gold and experience per minute. And finally, we have a hero suggestion tool, which we input the 9 given heroes that have already been picked, and the network will output a hero suggestion that can optimize the winning rate for that team. So for motivations, we are both crazy fans for Dota 2, and in daily life, we can make predictions about the game result based on our intuition and experience. So we want to see if a neural network can do the same.
So for part 1, where we just used the 10 heroes pick, we collected our own data from the OpenDota API. So for each call, it's called the public matches call. You can get 20 calls, you can get information on 20 matches, which have a bit more information that we use for data cleaning. So basically, we made sure the average MMR, which is the rank of the players, is above 4,500, which is about top 3 to 5% of all players. And we make sure that the game mode and lobby type is set to a ranking where, so 22 means ranking, where the 2 teams are more balanced, and the lobby type is 7, which is all picks, so that all heroes are available for picking. So after setting that, we got around 100,000 matches, and we found that there are some outliers where the average rank tiers are too low or the game duration was too short, so we removed those. And we also balanced the data to have the true and false for Radiant Win to be the same. So it's the same number of matches where the two sides won. And for pre-processing, we converted the hero picks to 1 hot vectors, and we converted the winning true and false to 1-0 for labeling. And after that, we have 90,000 matches for data, which we split it to 80% for training and 20% for validation.
So for part 2, the new features we're adding is a gold per minute and experience per minute. And so heroes can gain gold and experience by just killing enemies or pushing the towers, and they will lose it if they died. And also, GPM and XPM will relate it to the winning rate of the team, because if you have more gold and more experience, you will get better items and also stronger skills. This will help the heroes become stronger and more dominant in the game. And also, the reason we introduced these 2 features because they can partially represent the human factors on the game. And because of, for example, if a hero has more gold, it means that it wins most of the battles in the game. So it can represent that the players who control these heroes have a better game performance. So these 2 features we want to add the influence of a human's play into our network. So our data is collected from the Kaggle, and here's a data summary of the data set. So there are many features over here, and we only considered about the gold and experience over here. So these 2 columns will contain the gold and experience for 1 heroes across all samples. So we did the data cleaning, so we only use the gold and experience difference between the teams when the game is like 5 minutes. And we also do the data normalizing to reduce the actual influence on the data. And also the same we're dealing with the heroes as part 1, and also we'll do a train and validation split. So our model is pretty simple. It's a MLP, and because our input is a 1 hot vector containing the 10 picked heroes, and our output is just the probability between 0 and 1. For part 2, we also use the MLP, but this time our input is 1 hot vector plus these 2 new features, that is GPM and XPM.
So here are some hyperparameters we found to be the best, other than what the number of layers we use. And our results are here. So for part 1, our final validation accuracy was actually only 56%, but we were able to overfit our training data. So this wouldn't be really good if you consider it, because just by inputting all ones, you would get 50%. But so for part 2, we were also able to overfit, but we got 62%, so which means that putting in some human factor in would increase our results, so make our results better. So comparing part 1 to our baseline model, it did like 1% better than our baseline model. And comparing to others' work, most other works we found had around 60% accuracy, including those using similar methods as us. But we found this to be the reason since we collected our own data and we set some constraints. So for example, we only use players who had high skills, and we use only the newest patch, so version of the game that's played. And so for the newest version game that's played, everybody had a role, so people started to pick heroes with more sense. So I guess that's the reason we were doing a bit worse. So we used our result from part 1 to do predictor boss. So basically you can either input the 10 heroes that's picked in the game and it'll return you who's likely to win the game, or you can put the 9 heroes and it will return the top 3 heroes as suggestions. Yeah. Yes.
Thank you. Interesting. It was good to see the evolution where you started hunting up more the part 2, the second features. I like that. When you presented the results, what I wasn't clear on was were those 2 completely independent models working separately, or were they working together, part 1 and part 2?
Separately, but it was similar because we only added 2 features as human factors.
So the second model included the first model? The data?
In some sense. Like the input is similar. It's basically the same input from part 1, adding into.
Yeah. So it's, okay. So the same. So it was a superset of the inputs, part 2. So
Yeah.
So okay. That was good to see that thinking. Actually, I know we were trying to figure out how to do better. It sounds like it's a tough problem given what other people have done. What? Can you go back to that slide that shows the training, the validation accuracy of the part 2 model? Yeah, just you look at that and you go, oh, the training was really good at the beginning, and then it was overfitting, and the validation got worse. And you quoted the worst validation. You could do early stopping and pick the better one. We're all allowed to do that. So you could.
What was around like?
Looks like 65, not 62. I mean, it seems in this world that matters, given what you said other people do. So I would urge you to think about that in your final report. Mike?
Looks like you only had 2 splits of data. So are you confident that you didn't tune your hyperparameters to overfit on that validation set? Because you have no third set to look at.
Because we did a lot of hyperparameter testing. So maybe we can add it in our
I don't know.
report.
You do need to test it.
I would suggest it, yeah.
Those are the rules, right? Like the rules of your life if you want to be a machine learning engineer. Don't mislead yourself by over-tuning. And we've seen it happen already today once or twice. So. Okay, we should move on. Thank you.